arvoisa rehtori, professor, staff, students, and other members of the university community, guests and alumni, ladies and gentlemen. The topic of my Aalto talk is science, especially data-driven science. There has been a continuing trend in information sciences now for many years that most people probably don't know. Only quite recently we have heard a new buzzword, big data, which means very large and diverse collections of data on almost everything that can be somehow measured or captured. Large data centers are being built all over the world, including Finland. It might look like this is of interest only to software professionals, but actually it concerns all of us. First, some of that data actually tells what we are doing, how we use our computers, how we communicate using mobile phones. Second, based on that data, new services will become available that will be useful to all of us. Quantitatively, the sheer amount or number of bits of digitally stored data can be easily estimated. The amount of data stored by computer systems throughout the world has been exponentially growing, at least 30 years. The amount has roughly doubled every 40 months. Now, every single day, 2.5 quintillion bytes of data are created. That is 2.5 million bytes every single day. This is a staggering number. There is no reason in sight why this kind of exponential growth would not go on for some years at least. So it may be that in the future that number will look small. It will certainly have an effect on how information systems will be built, perhaps even on the way that research and development is done in companies and research laboratories. The young people that we are now educating will face new challenges and need a new set of skills when they enter the workforce. To take some examples of big data from social media, well known to many of us, in Facebook, 300 million photos and 4 million videos are posted every day. Twitter handles 400 million tweets every day. Google handles 2 million queries every minute. All these numbers are sharply growing day by day as more and more users get involved with social media. However, the main reason for the accumulation of huge data volumes are automatic sensor systems that just collect and store data for later use. Examples are surveillance cameras, industrial sensors, or mobile phone call detail records. Obviously, these big data masses offer a huge opportunity for studying the underlying phenomena. For natural sciences and engineering, it means more accurate solutions and new findings, perhaps even totally new fields of inquiry. But the research fields that may change most radically because of data-driven techniques are social sciences. For the first time, it may become possible to know on some superficial level what millions or hundreds of millions of people think and feel. We engineers can model a bridge or a car engine, but we cannot model the human society. There are no natural laws there like in physics. But with large amounts of data on people, new empirical findings may be possible. This is also a huge challenge, as we all know, because such data can be used in ways that touch upon the privacy of individual citizens. But we cannot think that data mining and profiling of people is inherently bad. We just have to be aware and careful how this information is used by companies and governments. What is perhaps more important for us working in the university laboratories is that science, too, has entered a new era, that of data-driven research. Information is extracted out of large masses of digital measurements, which is changing the very way that research is being done. Examples are physics, bioinformatics, brain science, astronomy, and climate research. The big question for us researchers is big data analytics. How do we cope with this data? Fortunately, also the raw computing power of modern computers has been exponentially increasing according to the so-called Moore's law, nowadays augmented by distributed and parallel computing systems like the cloud. So computers can in principle process larger and larger data sets. But the intelligent methods by which this growing data are analyzed has lagged behind. Scientific research is a human effort which does not proceed with exponential speed. Simple statistical methods developed many tens of years ago do not find the information buried in the data masses. We have to dig deeper. So what is urgently needed are more complex algorithms that yet would work fast enough to scale up to realistic problems. They would also need to understand at least something about the problem domain, the context of the data. This field of information science is called artificial intelligence. Here we can take some inspiration from the human mind, the human brain. On a subconscious level, our senses observe the world and the brain is able to transform the raw sensory measurements, like changes in light falling on the eyes, or pressure waves in the air reaching our ears, into meaningful concepts. Thus we understand what goes on in the world around us. Cognitive scientists are now starting to understand the basic aspects of this process, and it has become possible to form computing principles that somehow try to mimic human cognitive processes. These methods have such names as artificial neural networks or machine learning. I will give a familiar example. Think of internet search engines. You input some search words or phrases, and you get back a small set of meaningful pages. Now imagine that instead of text, your dataset would be videos. Now you cannot use a keyword-based search because videos do not contain text, just images and audio. So we would need to convert the contents of the video into textual keywords automatically in order to do search. This cannot be done manually because the amount of data is so huge. To do so, the computer software must be able to learn to recognize in human terms what goes on in the video, do pattern recognition. This is one of the research topics we have, and I believe you saw an example of this in the background video here. In the Center of Excellence of Computational Inference, or COIN, as we call it, we are working on this problem and many others. Examples are bioinformatics, for example, human pathogen evolution, neuroinformatics, or analysis of brain imaging, such as fMRI, and computational climate, or analysis of large-scale climate data to find meaningful climate components. All of these problems are based on very large data sets and require advanced and novel data analysis methods. Ladies and gentlemen, in my talk I tried to describe a world of the future, a world of big data. There are many hard issues here, from the problem of new intelligent data analysis methods to questions of privacy and data security. But big data is here to stay, and we have to live with it. So let us try to make use of it by making data-driven science one of the spearheads of Aalto research. It will be interesting, useful, and fun. Thank you very much.